Hello, Jacob. Are you there?
Yes, I'm there. I'm working on my network. We're starting soon. Just
Okay.
give me some few minutes. I'm having some network glitch. Like a minute. We'll start now. All right. Good evening, everyone.
Good evening. You're welcome.
Thank you all. Welcome to our class today. Probability theory and distributions. So, in this class, we'll be taking an introduction and also a deep look on the aspect of probability theory and distributions and how they are important, their relevance, and how we can use them in various ways. We'll also be looking at the mathematics behind them. We will be looking at different probability distributions, ranging from the discrete probability to the continuous probability distributions. We will see how we can apply or how each of these probability distributions are applied. We will also be looking at how we can generate their moments, their expectation, which is the mean. We will look at the first moment. We will look at the moment generating functions, and then we will look at some other uh, things that relate to probability distribution and theory. So in our class today, we will be starting with the introduction to probability theory. We'll be looking at some definitions of probability, some axioms, and then we'll get a general overview of what to expect in probability theory and distribution. We'll be taking this course together with Ilyasu. Now, the lesson outline for this particular lesson, which we'll be taking from this week to the next week, will include definition of probability, the classical and relative frequency approach to probability. We will also be looking at axiomatic approach to probability. That's the various axioms of probability. We will look at Bayes' theorem and its application. We will also look at the expectation of a random variable and its properties. And then we will look at moment generating functions, MGF, their properties and their uses. So this is basically the overview of uh, what we'll be looking at in this course for this week and next week. But for today, we will be looking at the definitions of probability, some axioms of probability, the classical probability. We will look at events, mutually exclusive events, and non-exclusive events. We will also look at the relative frequency probability, that's its definition, and then we will venture into some examples. All right, so permit me as we start. So let S, comma A be a sample space and a collection of events, that is subsets of A. We know that if we have a set, the universal set, which is S, is a is a universal set, and then it's also a subset. And then we also have another set A, which is a subset of S. So uh, these two values in bracket, S and A, where S is a universal set and A is subset, we say let it be a sample space and a collection of events. That is subsets of S. Now, a probability is a function P that assigns to all events a number between 0 and 1. Now, we know that we're used to the normal definitions of probability, but here we want to go mathematically. So that's why we're defining probability in this way. Now, mathematically, we say P such that this column means such that. So we read this as P such that A maps in the range 0 and 1, such that the two axioms of probability hold. What we are trying to say here is that A, if A is a subset of S, then A must lie between 0 and 1, which means that any calculation that we, or simply any calculation that we can do of any subset of a universal set, the answer must lie between 0 and 1. Now, such that the two axioms of probability hold. So we have two axioms of probability here. One, it says that the probability of S is equal to 1. What that means simply means is the probability of a sample space, just like we have explained before, that S here is a universal set or the sample space. And a sample space is a set of all possible outcomes in a probability. So the probability of S is equal to 1. So that's the first axiom. We should put that in mind, that if we take the probability of all set of possible subsets of a universal set, it is equal to 1. We will get 1. Now, the second axiom is state that the probability of A union of A1, sorry, union A2, union A3 continually to union AI. That's we're saying that if you take the probability of all the unions of the possible samples in a sample space, the result is equal to the sum of the probability of all the individual AIs. We say AI where A ranges from A1, A2, continually to AN. We say they are what? Mutually exclusive events in A. So these two axioms, we'll be looking at them as we make reference as we continue in this course. Now, any definition or interpretation of probability that we come up with must satisfy this definition above that we give. That is this definition. We say that if you take the probability of of an element of an element of a subset, it must lie between 0 and 1. And we also say that this axiom must hold. That is, the probability of all the sample space must be equal to 1, and then the probability of the individual union of the sets must equal to the sum of the probability of all the individual AIs, provided that A1 to A1, A2 to AN are mutually exclusive. Now, what are mutually exclusive events and mutually non-exclusive events? Mutually exclusive events are events that their occurrence does not affect the occurrence of other events. Let's take, for instance, the toes of a feather. The probability that one will show up uh, is not affected by the probability that two will show up or three will show up or otherwise. Now, so we say any definition or interpretation of probability that we come up with must satisfy the definition above. One possible definition is the classical definition of probability. For simplicity, we will look at discrete sample spaces, that is, sample spaces of the form S equals S1, S2 to Sn. By discrete, we mean something that is not continuous, is countable. In this case, we can take a sample space A is to be, sorry, we can take an event A to be the collection of all subsets of S, which we will implicitly do throughout. Now, the first definition, we'll look at the classical probability definition. Now, the classical definition of probability assigned to an event A as a subset of S, the number. Probability of A is equal to the absolute value of A over the absolute value of S. Now, here, the absolute value of A means the number of elements in the set A. And then the absolute value of S also means the number of elements in the set S. So when we take the probability of A, the classical approach says that we will take the ratio of the event A all over the total sample space. Now, let's first check that this is a probability in the first place. And we'll do that by looking at our axioms that we have seen above. Now, we'll see. Since A lies between 0 and S, obviously, A will lie between 0 and S because A is a subset of S. So there is no how A will be 0, and then there's no how A will be more than S. Now, since A is a subset of S, it always holds that the probability of A will lie between 0 and 1. These are 0 less than or equal to probability of A less than or equal to 1 means the probability of A lies between 0 and 1. Here, 0 is less than or equal to probability of A. Probability of A is less than or equal to 1. Now, furthermore, the two axioms are satisfied, as we can see below. Now, like I explained earlier on, when we see this A, this this object that looks like C with an underline means subset. All right. Now, we see that from the definition of classical probability above, we see that we will see that the definition of classical probability satisfy the axioms that we have mentioned when we were defining probability in the beginning. So we see one, when you take the probability of S, it will equal to the number of the number of events in S over the number of elements in S. Here we are saying when you take the number of elements of both of the total sample space, you will get 1. 2. Let A1, we say A1 is an event in S, like we have defined above. Let A1, A2 continually to AN be mutually exclusive. By mutually exclusive, we mean that the occurrence of one does not affect the occurrence of the other. Then, here we see that the probability of A1 union A2 union continually to AN will give us what we have here, the number of events in A1 union the number of events of A2 continually all over the sample space. So here union we have the number of events in A1 plus A2 continually all over the sample space. So when we do that, it gives us the sum I ranging from 1 to n of the probability of all the AIs, which are satisfy the axiom that we have above. Now, we can check the second equality by drawing a Venn diagram. So when we do that, we can get more insight. In order to make the step to the relative frequency definition, note that we can write the classical probability in the following. For every possible outcome, S of I, sorry, this I is supposed to be subscript. S of I, which means S of I means where I ranging from 1 to n. We are saying S of where when we have S1, S2, S3. So we're saying if we take an event from the total probability, which is S, I can define the number that is P of I equal to 1 all over the total probability. This indicates that we assume that every outcome is equally likely. Then we can recover the classical probability as follows. So here in equation 2, we have the probability of A is equal to the sum of all the individual probabilities. Just like we have seen above here, we say P of I is equal to 1 over S, and we know that the total sample space is of S, number of S is 1. So when we divide, we get 1 here. Now, since the sum of P of K is equal to the sum of K belonging to A, 1
Hey,
all over.
Jacob.
Yes.
Ilias's hand is up.
Okay. Ilyasu, let's
Yeah,
hear you.
sorry, just a quick maybe question.
Okay.
Here when you said equally likely for all the event have equally likely. So what maybe you can explain better.
Okay.
Just for people to recall,
Okay.
if we are defining a classical and the frequency definition of probability, so when events are equally likely, they have all equal chances of occurrence.
Okay. Okay.
For example, if you toss a die once, the probability, let's say it show 2, is
Mm.
equal to the probability that in another
Choose
event
one.
tossing it show
Yes. Or
another
every
number.
other value.
That is a standard classical definition of probability by frequency approach, right?
Yes.
Yeah. Okay. Please go ahead.
All
Thank you.
right. Thank you for that insight. So let's continue. Let's look at this example here. Consider the experiment. Roll a die. Here, the die is a fair die, so that will make the occurrence of each of the events to be equally likely, just like Elias has pointed out. Because if the die is not fair, then the chances of occurrence will not be equally likely. So if we roll a fair die, now the sample space here, it is either a 1 or a 2 or a 3 or 4 or 5 or 6 shows up or it occurs. We know a fair die, right? A die, that uh, cube that we use in Ludo game. Yeah, so if the die is fair, it means that all the values are there, 1 to 6. So when we toss or roll a fair die, we have equally likely chances that 1 or 2 or 3 or 4 or 5 or 6 appears. Now, in the classical definition, in 1, the probability of the event A, that is an even number occurs. Here, we see that the probability of an even number occurring means that it is either 2 or 4 or 6 occurs. Whereas the probability of an odd number occurring, it is either 1 or 3 or 5. So If our interest is the event A such that an even number occurs, which is either 2, 4, or 6, then our from the classical definition of probability, our probability of event A occurring give us what we have here. That's the number of remember we say the absolute value of A means the number of times it occurs all over the number of times of the whole sample space. So for the event A, we have that the even numbers that occur are 2, 4, or 6 over the total sample space, which is either 1 or 2 or 3 or 4 or 5 or 6 occurring. Now here we see that we have 3 over 6. When we do the division, we get 1 all over 2. So therefore, the probability that event A occurs is 1 over 2 or 0.5, as the case may be. Now, using sorry, now using 2, you first have to realize that all k in A are 2, 4, and 6, just like we have just like we have explained k there up. We say the k of A in A are 2, 4, and 6. So we're still solving what we have solved up, but we're trying to show using the classical definition of probability. So if we take the probability of each of them equally likely occurring, we have the probability of P of 2, that's P subscript 2, which is the first even number to occur, is 1 out of 6, plus the probability that 4, which is the next even number occurring, is also 1 out of 6. And then we sum again with the probability of 6, which is the third even number occurring, which will give us 1 over 6 as well. So when we do the math, we get 3 over 6, which is 1 over 2, or 0.5, as the case may be. So we see that the definition in 1 and 2 give us the same answer. That's if we take if we take them all together or individually, we'll still get the same answer. Now, the formulation 2 now give rise to a more general definition of probability. Now, instead of assign P of 8 equal to 1 over S to every point, we can use any number between 0 and 1. This allows us to model experiments where not every outcome is considered equally likely. So if we are faced with an experiment where it is not every outcome that is considered equally likely, we can also assign P equals 1 all over the number of every possible outcome. So this will lead us to this following definition, which is the second definition, and it is based on the relative frequency probability. Now, the definition goes thus. Let S be equal to S1, the set of, this curly bracket means set. So let S be the set of S1, S2, continually to Sn, be a sample space, and let P1, P2, Pn be such that all Pi are in this are in 0 and 1, are in this interval 0 and 1. Now, what this means is that we're saying that if you take individual probabilities from P1, P2, P3, just like we have defined earlier on, we say it must lie between interval 0 and 1. And we also take the summation of all the probabilities from I ranging from 1 to n, we will get 1. Just like the first axiom that we have seen above, we see that when you take the probability of all the sample space, you get 1. And here we see that if we take the sum of all individual probability, given that it's possible, it is going to give us 1. Now, the relative frequency probability assigns to every event A the probability that P of A, which is our equation, P of A is equal to the sum of all K belonging to A. That's we say A is a particular event that we define of the summation of all the probabilities. This is our equation 3. Now, it is immediately clear that the classical definition is a special case of the relative frequency distribution. So when we just take the first probability equal to the second probability, that's probability of first event equal to the probability of second event, and so on and so forth, it will give us 1 all over the number of all the sample spaces. Now, the conditions that are put on the numbers, that's probability from P1 to Pn, which can be interpreted as the probability of each possible outcome occurring, we ensure that 3 here is a probability. Now, obviously, probability of A is greater than or equal to 0. Like I've explained there, we say it is either 0 or greater than 0, and it is either 1 or less than 1. So here we see that probability of A is equal to the sum of the probability of individual case, which is less than or equal to the summation of the individual case. Sorry, here K belongs to A, which is the probability of a particular event from the total sample. We say it will be less than or equal to the probability of events of the total, which is equal to the summation of K ranging from 1 to n of all the probabilities on the individual probabilities, which will give us 1. Now, where the inequality follows from the fact that A is a subset of S, and the final equality follows from the restrictions we put on the individual probabilities. Now, furthermore, the P satisfies the axioms of probability. So the axioms here, just like we have explained on top. So we see this axiom is a bit different from the one we define when we're introducing probability. So here, the total probability
So someone
is
raised their hand. Sorry, Jacob. If
yeah,
you can maybe focus on those raising their hands up. I can see Adebi has raised her hand up. If you can just attend to her,
Yes, thank
please.
you, Elias.
okay,
If it goes back to the last slide, the slide before this one,
okay,
yeah. I just feel that if a more practical example is given here, uh, because there's something going on in my brain that I felt maybe it's right. I
okay,
know that the probability of this A event, which is the event of even numbers occurring from the sample space of the fair dice,
yes,
is equal to the individual one, which is the individual number, I mean the even numbers, which is 2, 4, 6 this time around. But
yes,
this place here, I know it's going to be less than, because in the sample space we have 1, 2, 3, 4, 5, 6. So the odd numbers will be the other part. Actually, this will be less than. And for it, I'm just trying to use the example of the fair dice. So for this condition to be satisfied, it shows that maybe we have to use another example, or we have to define another element in a way that we can take care of the odd numbers, so that the addition of all the odd numbers and the even numbers will give us 1. Or we use another example to kind of that will enable us to know when this condition is satisfied. I'm sorry, I thought I'm sharing my screen, but no, where this next assumption of summation of pk, k going from 1 to n, is equal to 1, is satisfied. If you can, we can put a good picture of a practical example. That, I'm sorry if I can put it properly.
Yeah, I understand. Yeah, there's an example that we're going to see below. Maybe when we solve that example, you get more clarification.
Okay, all right.
Thank you.
Yeah, I mean, so yeah, for the future, in every step, for example, in this kind of example or definition,
Yes.
you can put like uh,
An
example
example.
for them to see, because it's kind of abstract, you know.
Yes, yes, yes.
Uh, yeah, some may forget, and just to recall how it looks.
Okay.
And most people that study statistics are more or less on practical things, what they can see. But I know people that do pure mathematics, I mean, see this very clear. But
Yeah,
yeah, all good. So thank you.
it's all right. Thank you very much. We will look into that in our subsequent classes,
All
and
right,
we
thank
will
you.
we'll try to put more practical examples so
Mm,
that it will give us more idea
yeah.
on what we are saying here. All right, so can we continue?
Yeah, thank you.
You're welcome. All right, so we have explained this before, so we'll just move to the next slide. Now, example two. Suppose you have conducted the experiment of rolling a die 1,000 times, now resulting in the following bar graph. So, looking at this bar graph, we have conducted rolling a fair die 1,000 times, and it gives us this particular bar graph. Here, we see that a 1 has a relative frequency of 0.5, which means a 1 occurs like half of the time, of the whole time when the die was rolled. Here we see, and half of the time that the die was rolled is 500 times. Here we see a 2 uh, having a frequency of almost 0.1. That's like 100 times. We also see, which is also the same for 3, 4, 5, and 6. Though for 4 and 5, it looks a bit higher. But we are not actually interested in the exact value, but we're trying to see, have an idea or a picture of the definition of relative frequency that we're talking about. Now, it is obvious that not every outcome is equally likely, and that therefore the model P1 equal to P2 all equal to P, that's 1 over 6, which is the classical definition, is not an appropriate choice to model the randomness in this situation. So this next, the example we give in 2 of rolling a fair die 1,000 times, if we want to adopt the classical definition of probability to solve it, it may not be an appropriate choice to model the randomness, because this situation is a bit different from uh, the first example that we have when we roll a die once. Now, since you observe that the outcomes 2 to 6 appear to occur pretty much equally frequently at around 10% of the time, whereas the first outcome occurs more frequently, you are driven to take P2 from P2. Let's say we take from P2 to up to P2, P3, up to P6 to be equal to 1 all over 10. And then hence, P1 is 1 all over 2. Just like we've seen there, that P1 takes like half, occurs like half of the time. Now, letting event A, to be the set of even numbers, that's 2, 4, and 6, we will find that the probability of even number coming up equals uh, if we take for if we take individually, that's for 2, 1 all over 10, for 4, 1 all over 10, for 6, 1 all over 10, and we sum all of them, we will get 3 over 10. Now, in addition, if we let B, that is the sum of odd numbers occurring, which gives us the set 1, 3, and 5, we will find that the probability of B will now be the other uh, part of the probability of A. Since we have the probability of odd numbers, even numbers occurring to be 3 over 10, then we have that the probability of odd numbers occurring 7 all over 10. So here we have 1 all over 2, that's 1 occurring, plus 1 all over 10, that's for the other uh, 3, and then 1 all over 10 for the other 6. So this gives us 7 all over 10. So the probability of even numbers occurring is 3 over 10, and the probability of odd numbers occurring is 7 over 10. Now, all right. So this example shows that you choose the probability. If we are choosing to apply the classical definition of probability, we'll have had to conclude that events of an even or odd number or coming up are equally likely. Now, in light of the bar graph that's plainly wrong, here we see that a first link between statistics and probability, a bar graph or histogram, can tell us something about how to choose the probability P. So, summarily, just like we said in the beginning of a class, that today's class is more like of definitions and just a brief background of probability and some axioms of probability. Uh, we will just take the summary. First, we define a probability mathematically. We also give some two axioms of probability. We say that if you take the probability of the total sample space is equal to 1. And then we also define the classical probability. We explain an event. We said that an event is said to be mutually exclusive if the occurrence of one does not affect the other, and then it's said to be mutually non-exclusive if the uh, occurrence of one affects the other. We also
Sorry, just a quick observation. I'm sorry for
okay,
interrupting you.
okay,
Yeah, so in probability theory, I think some people misunderstood differences between independent and dependent events.
okay,
So they define mutually exclusive event as independent event, like saying probability of event A. For example, if A and B are set, probability of event A will not affect probability of event B. No, I think the way the thing is, uh, when we say they are mutually exclusive, it means they cannot just occur at the same time. That is mutually exclusive. The other definition that, for example, let's take an example of a healthcare. When we are pricing a health insurance product, and then we want to, for example, someone that has malaria uh, have chances of maybe showing up for treatment of headache, for example. So
mm,
you see that there is like kind of connection, there is dependency. So if we try to put together all this, considering all this, for example, we say, okay, pregnant woman, there is high chances of pregnant woman to fall for malaria sickness. So like this is dependency, not mutually exclusive. So if we are trying to model, we just assume that they are independent. All the events are independent. For example, someone having malaria, someone that is pregnant does not mean he will have malaria. But in real life, we see that these two are connected and they are very, very related. Yeah.
exactly.
So that is dependency.
Mm,
So when event A and B are independent, means event A, occurrence of event A will not affect occurrence of event B. When they are mutually exclusive, it means that event A and B cannot occur at the same time. So that is just my comment on the definition of the definition of inclusive and the exclusive
Okay. Thank you.
event.
Thank you, Ilyasu, for shedding more
Yeah.
light. Actually, I was getting to the point of allowing you to say, uh, to pick up from where I stopped. So when I finish the summary, I'll give you the chance to add more.
Yeah.
Oh,
Hey
sorry.
Jacob,
Please,
someone's hands
before,
up.
yeah, thank you very much, Alimat. The slide before this summary, you made a comment about, I think the second, the second paragraph talking. Yeah, you said that we should learn to choose how to choose our probability. Can you shed more light on that? Uh, Tell us something about how to choose
Okay.
the probability, something like
Okay. Uh, what the statement is saying is not that we should learn how to choose the probability, but it's saying that uh, the example we give above
that. Yeah,
was actually formulated.
okay,
Do you understand?
yeah.
Yes, it was actually formulated.
And so, what? How does that goes with? Should is that? I'm sorry. I'm just trying to go with what I'm reading. That you choose the problem.
Mm. Do you understand? What that statement actually means is that we that bar uh, that histogram
Yeah,
we showed was actually uh,
it
was
was
actually assumed
okay.
or
It was
formulated.
made on assumption.
Yes.
I thought it was okay. So it wasn't a real event.
No, it wasn't a real event. It
Okay,
wasn't a real event. Yes, so
okay.
that's the meaning of the statement.
So can we say that is the event is not fair, or is it that such thing cannot happen, or is it an outlier or something like that? I just
Yeah,
want to put a
we
practical.
can say it may not happen. You understand? It's just like it's an example to
So
give
an
us more
outlier,
insight.
it might not really it's one in thousand, something like that. It might not really happen. Something.
Yes, yes,
Okay,
yes.
thank you.
All right, Bello, you're raising up your hand. Go ahead, please.
Hey Bello, we can't hear you.
Hello, Bello, are you there? All right. If Bello is not there, at this juncture, I'd like
You
to.
can use the message box, Bello. If we can't hear you, if you're having a problem to talk, you can use the message box.
Yeah, and it seems he's on mute. Probably some technical issue.
Mm.
Yeah.
So that'll be all from my end for today. So I'll hand over to my co-instructor, Ilyasu, if he can
I mean,
shed more light
we
to
just
what we have shared today.
maybe someone have some question before any other thing, and
So
if
am
everything
I
is
still
clear.
not clear, or is it better now?
Yes, I think yes. Now I can hear you.
Okay, thank you. So I say, if I'm allowed, just also a little contribution, and you can
Mm-hmm.
correct me if I'm wrong. And this is in response to Adebi's questions. I'm looking at if we are talking of mutually exclusive and maybe independent events. If I have a jar, and in that jar, maybe I have seven white balls and three black balls. That is 10 balls in all. At any point
Mm-hmm.
in time, if I want to pick a white ball, the probability of picking one ball at a time, if it is going to be white, 7/10. If it's going to be black, 3/10. And if I'm looking at independence, if I pick and I return and I pick again, so the probability of the white will always be 7/10, and that of the black will always be 3/10, and they are independent.
Yeah.
But if I pick without replacement, I pick the first one, the first probability will be for white 7/10, and for black 3/10. So if I did not replace and I have to pick the second time, the sample space, if I can borrow from what we learned here today, on my second picking, the sample space has changed and the composition has also changed. And
Yes.
so the outcome of the second item is dependent on what happened in the first item. The second picking, the probability is a function, it depends on what happened in the first pick, whether what I picked was white in the first pick or black in the first pick. So while this discussion was going, I just quickly put this in my head, and I don't know if I'm right, I don't know if I'm wrong. I just feel like bringing it out there. You can correct me if I'm right or wrong. Thank you. Hello?
Yeah.
Yeah.
Jacob, you have something to say? Oh no.
No,
Go ahead.
Elias, you can pick from there.
Yeah, you are right, Mr. Bello. I mean, when we are defining independent event, like it's something on its own. So this replacement or without replacement is a condition. So if we put the condition of with replacement or without replacement, of course we can define, it will have a different shape and a different definition.
Yeah.
Just like the example you cited. But in general, if we are defining an independent event, it's just a simple word that the probability of one cannot affect the probability of the other. I mean, so the probability are entirely different. So that is what independent mean. But if we have a particular case in which we talk about with replacement or without replacement, then that is, I think, a different thing on its own. Yeah, so it's a condition. If you put it in your statement, then it has to be mathematically justified.
All right. Thank you, Yasu,
Yeah, so
for
I don't know if it makes sense.
Kainde. Are you satisfied?
Yes, I'm okay. I'm okay. Thank you.
All right. Thank you for your question. So, Eliasu, you have more to share before we.
No, nothing from. I mean, what time is this class supposed to end?
Let's say 8:20.
Sorry for. Okay. I
Yeah.
just
And
missed it.
since today is the first class, uh, we just want to take an introduction so that we get some definitions and then have a background and a compass where the direction of the class will be going to.
Yeah. Okay. So in case of the next class, please, Yakub, if you are preparing the slide, give more like examples in practical sense.
Yeah.
Especially now, we are focusing mostly on insurance
Yes,
stuff.
yes, yes.
So if you can give example on that, that would be great.
Yeah, so that it will be easily relatable.
Yeah. Okay, and more real life. I can understand this is just an introductory class. So guys,
Yes,
yeah, there are more expectations, so more to come.
yes.
And thank you all for joining. I need to drop
Any
now.
any more question from
Have any
anyone?
question, please ask, or any comment, observation. Mr. Osahon, how is it going today?
Yeah, I'm fine. Thank you very much.
Yeah, thank you.
Yeah, thank you very much.
Yeah, so who else? So yeah, everyone is here, and thank you, Mrs. Adebi. Miss, sorry, Adebi. Yeah, hope I get the name right. Always.
Okay. Is that it for
All right.
today, please?
Yeah, that's it for today. We were supposed to give some exercises, but since today's class is more like an introduction. We just want everyone to go and read more on mutually exclusive events and non-exclusive events, independent events, and then others. We should also look at the axioms of probability more closely so that we will get more understanding. So in our next class, we'll be looking at uh, Bayes' theorem and its application, expectation of a random variable and its properties. So uh, thank you for the question. If we go through the learning system, we will share more materials before the next class so that we can look at them.
Yeah, sorry. For the next class, we'll share material. I think our Jakub will update. Sorry, will upload those books that
Yes,
are relevant. So yeah,
yes.
and those will have practical example.
Thank
Yeah.
you.
So in case, and one more thing, in case you have some challenging problem somewhere, you stumble on it or from your work related to probability as far as the course is concerned, please bring it. Then we can have a look also,
Thanks.
because that is why we are here. It's kind of more professional. We are just building our professional capacity in general.
Okay. Thank you very much.
Thank you.
Yeah.
All right.
Thank
Bye,
you.
everyone.
All right, thanks
Bye.
everyone. Do have a great night. We'll see you in the next class.
Shar Habi, are you here?